Very good afternoon, students. So today we are going to perform our seventh experiment. The name of the experiment is the design and analysis of full wave rectifier with and without filter. Okay. So full wave rectifier can be performed or it can be constructed by two types. Okay. The first one is center tapped full wave rectifier. Okay, and the other one is bridge full wave rectifier. Okay, so here we are going to perform center tapped. Okay, so now what is actually a center tap full wave rectifier? Okay, firstly you must know that a full wave rectifier is that type of circuit which rectifies both the positive and the negative half cycle, okay, of the input signal. Okay, as we have seen that in the half wave rectifier, what we got only the output cycle for the positive half cycle of the input. Okay, but in this case, in the full wave rectifier case, we get output at both of the half cycle of the input. Okay, that means that for the negative half cycle and for the positive half cycle. Understood? So just I am going to show you the construction here. Okay, the circuit diagram. In that thing I will let you explain that what is the center tap transformer. So this one is center tap transformer. Okay, both there are two input. Okay, just see here both the inputs here. Okay, now here in the secondary winding, what happens actually? Okay, in simple transformer we see that there are two output wires. Okay, this one and this one. Okay, in the simple transformer. Okay, but in center tap transformer, at center of the winding also, here also, at the midpoint of the secondary winding, understood? At this point it is tapped and a wire is taken out from that thing. Okay, so what happens now? This point forms a neutral. Okay, because the voltage at this tap point is 0. Understood? And both of these half are having separate output voltages. Both are equal. Understood? In magnitude, but opposite in polarity. Remember this thing, that this half and this half, both the half are having equal output voltages which are equal in magnitude, but remember these are opposite in polarity to each other. Okay, so this is what the center tap is all about. Okay, so this is a simple overview of center tap transformer. Okay, now what happens actually when we provide input cycle to the primary winding of this transformer? Okay, in one case what happens, D1 diode comes and acts as a forward bias condition, and when it acts in forward bias condition it thus passes the current through it. Okay, understood? And this thing I have connected it to the load, that is RL. Okay, and here the other end of RL is connected to the needle, that is center one this transformer. Okay, so we are going to take the output across this RL. Understood? The positive wire I will connect here at this point of RL, and then other one of the oscilloscope wire in which I am going to see the output, I am going to connect it in the neutral part of this transformer. Okay, now in the second part, this D2 diode acts as in forward bias condition, and this D1 acts as in reverse bias condition. So this will not give any output, but this D2 will give the output here. Okay, so in that case, just see here, for the negative half cycle of input I am getting this positive half cycle of like output. Okay, this for this positive half cycle I am getting a half cycle output here, and for the negative half cycle of the input I also am getting positive half cycle here. Okay, why? Because the diode D2 comes in under the positive half cycle under the action of forward bias condition, and it gives us a positive output signal here. Okay, in for this negative input half cycle. Okay, so this is what this whole circuit is all about. Now here also I am seeing that I am getting a pulsating signal here. Okay, so this could not be used for the DC devices directly. Okay, it is having many ripples here. Okay, this is a pulsating signal. So what I am going to do, I am going to add a capacitor here across this RL. Okay, I am going to add a capacitor here. So just see, when I am going to add the capacitor here, the ripples mostly it would be gone. Okay, so what would be the value of capacitor which I am going to use? Okay, these things you will learn in the theory, but I will tell you while we will perform the experiment, that what should be the value of this capacitor, so that this ripples could be eliminated, okay, fairly, so that we could use this output signal in our devices. Okay, so this is what the experiment is about. So just see here, I have written here the theory also. The full wave rectifier is a type of rectifier which converts both half cycle of AC signal into pulsating DC signal. Okay, so in this type of circuit I am going to use two diode here. Just see here, since both of the diode are going to give us the output here. Okay, so here this is the whole of the process, okay, that how the circuit actually works, which already I have told you. Okay, so now I am going to perform this experiment and I will start my multisim here. Okay, now I got it. So here I am going to perform this thing. Okay, so this one is the layout of the breadboard here. Now I am going to firstly check here a power voltage source here. Okay, so for that thing I am going to take a AC voltage source here. Okay, this thing I have taken. I am also going to take a ground here. In sources only I will take the ground. Fine. Okay, now I need to take a transformer. So I'm not going to find that thing here. I'm just going to write here transformer and it will find that thing for me. Sorry, transformer. Okay, transformer CT rated is center tap. Okay, so just see here, I have taken the transformer here. Okay, now I am going for the diode. Okay, so for that thing I am going to use 1N4007 G. Okay, so just see here, I am taking one diode more. Okay, so for both the half cycle I have taken both the diode. Now I am going to take the resistance here. Okay, I will take of 1 kilo ohm. Okay, so it is not coming because 1K value would be of many kind of equipments, okay, such as capacitor, resistor here. So for that thing I am going to just move on this basic part. In that thing I am going to choose the resistor here. So this is 1 kilo ohm already here, so I am going to use here 1 kilo ohm resistor. Now all of these things I have done, so I am going to close this thing firstly. Now I am going to add these things. Okay, so for firstly I am going to add this AC signal to the primary winding of this transformer. Okay, now I am going to add this one, the output, the secondary of the secondary winding here to both the diode. Okay, okay, fine, it's look good now. Okay, so here I am going to add a resistor here. Okay, so I have added a resistor here, and now the resistor other end I am going to connect here. Okay, so this is our circuit here currently. Now I am going to add a ground also here. Okay, and this part. Okay, so for ground I am just going to, sorry, I'm just going to take the ground here. Okay, okay, now it looks good. So this is our circuit part. Okay, now I'm going to add here oscilloscope also in order to take the output. Okay, So one output I am going to take at one end of the register and other output I will take at this end. Okay, so first output at this point. Okay, you could add this wire here, here or here. Okay, it will not make any difference. And the other part I am going to take it from this other end. Okay, that is ground. Okay, so now I am just going to run this circuit. Okay, so now for display purpose, one of the input of this oscilloscope I am also taking from the input source here. Okay, here I am going to take it from here only. Okay, because of the transformer turns ratio, this voltage is already being lowered. Okay, since this is a step down transformer. Okay, so this voltage would be lowered here. Okay, so whatever voltage I am going to give here, okay, this transformer will give some lower voltage. Okay, you have already learned about the step down transformer and step up transformer here. Okay, so firstly I am going to increase this value. Okay, suppose I am going to use here a 4 volt RMS value. So in peak to peak value, that would be 4 into 1.414, that would be around 5.6. okay, 5.6 volt peak to peak. Okay, approximately. Okay, and this frequency, let this frequency to be low also, around just 50 hertz. Okay, so now this one is over, and this negative end I am going to connect here to the ground. Okay, or I could directly simply connect it to here only. Okay, because this wire is already connected to the ground. Okay, so now I am going to run this simulation. Okay, so now I am going to check the output here. Okay, so since both of these are of red color, so firstly I am going to change one of the wires here, the color one. Okay, so I am going to change the color of the output wire. I am going to take the blue one. Okay, so now I am going to run the simulation. Okay, so I am unable to see the blue one, so I am going to reverse this thing. So now you can see both of the input and output one. Okay, so now firstly I am going to pause this thing so that you could look it clearly, and I am going to decrease this division, voltage division of both the channels. Okay, it looks good now here. So just see here, this red one is the input signal and this blue one is my output signal. Okay, so you can see here, for positive half cycle of input I am getting the positive half cycle of output, and for negative cycle of input also I am getting a positive cycle of output here. Okay, so now but you are seeing this the voltage of this output signal is little bit low from that of the input signal. Why is this? Because there is a voltage drop because of the diode which we have used. Okay, around 0.7, 0.5 to 0.7 volt, it would be there anywhere. Okay, 0.75 to 0.7 volt, it could be anywhere between these two values. The voltage drop down is there. Okay, but you can see the time period here. Okay, this one. Okay, so the output is having the time period of half. Okay, so now what I'm going to do, I'm going to measure the efficiency of this full wave rectifier. Okay, and you all have to measure the other different values, the ripple factors, the other different values. Okay, so for that thing, just see here, I have given the formula here also. Okay, it's the formula of efficiency here. Okay, so it is power DC divided by power AC. Theoretically it is 0.81. Okay, that is 81%. Okay, so for that thing PDC I do need to take the value of VDC here, and for power AC I do need to take the value of VRMS here. Okay, so VRMS is Vmax divided by root 2 and VDC is 2 Vmax divided by pi. So for both the thing I need to find the value of Vmax, that is the maximum voltage of output signal. Okay, so for that thing what I am going to do, I am firstly going to remove one of the signal here, and then I am going to calculate the value here. Okay, so for that thing what I am going to do, I am going to stop this thing, and I am going to remove one of this input of this oscilloscope. Okay, now I'm going to run this thing. So just see here, I am going to increase this division, sorry, decrease the division here. Now it looks fine. Okay, so I'm going to stop this thing. Now I'm going to use any cursor, suppose here. So yeah, this is the maximum point of this output signal voltage. Okay, so here in the T2 I am going to see here that it is 848.127 millivolt. Okay, so that thing I am going to write here, and where in the notepad it is 840, sorry, it is 848. Okay, around 848.127 millivolt, 848.127 millivolt. Okay, so this is the voltage of our output signal. Okay, so this one is the Vmax. Okay, so we have calculated our Vmax. Now what I'm going to do, I am going for the calculator and I will measure the value of both the VRMS, the voltage RMS here and VDC here. Okay, so by using a calculator we can calculate this thing, the VDC and VRMS, and then we will use this formula, okay, to get the value there. Understood? So just see here, I am going to find the value of VDC here, okay, and VRMS here. Okay, so for VDC it is 2 into Vm into pi divided by pi. Okay, so the value is 842.127, okay, millivolt. So I will just take the value in millivolt only. Okay, so the VDC is Vm into 2, okay, divided by pi is 3.14. okay, so this is the value 536.383, okay, which I have got here. So I am going to write here 536.383, 536.383. okay, you don't need to take 3 digits after decimal. Okay, it is not required, this will work only. Okay, so this is our voltage DC. Okay, so VDC is this one. Okay, so I will just use caps lock for V. Okay, so with this VDC I have got it here. Now I am going for the VRMS. Okay, so for VRMS what I am going to do here, I am again going to take the value of this thing 848.12 here, 848.12, this thing I am going to divide by root 2. So the value of root 2 is around 1.414. okay, understood? So this will give us the value of the VRMS. So it is 599.80. So VRMS is around 599, okay, 0.80. So these are the value of VDC and VRMS here, which I have got, okay, by the help of my calculator. So now what I am going to do, I am going to find out the value of PDC divided by PAC. Okay, so for that thing, when you will divide this PDC divided by PAC, this RL and RL would cancel out. Okay, because the RL value is 1 kilo ohm. Okay, simply we are going to we are left out with VDC divided by VRMS whole square. Okay, so what I am going to do, I am going to divide the value of these two and I am going to square that value. Understood? So for that thing again, what I am going to do here, I am going to use here calculator again, and now what I am going to do, I am going to divide both the values which I have got, this divided by this, and then I will square that value. Okay, so the value is 536.38 divided by 599.80. okay, so the value I have got is 0.89. understood? 0.894. So I am going to square this thing. So just see here, the value which I have got is 0.799. Understood? So 0.799, that means approximately 0.80. Okay. So that means I have got the efficiency n of around 0.79. So just see here, theoretically the value is around 0.81. Okay, and the value which I have got here is around 0.709. So that will be approximately equal. Okay. So if you just multiply it by 100, you will get the percentage here. So we have got around 80% of efficiency. Okay. So you have to find the ripple here, the ripple factor also by your. Okay. I will not do that part. Okay. That you have to do by your own. Okay. You have to write the precautions, the result, whatever you have got. Okay. Now one thing I will show you in this multisim. Okay, so this the value of this output voltage is 848.12 millivolt. Okay, so I am going to show you that how much the voltage of this output one is lesser than that from the input voltage. Okay, so for that thing I am going to just remove this part of this oscilloscope, and again I am going to connect a wire from oscilloscope this end to input one. Okay, so now this is my wave here. Okay, so justly I'm going to just stop this thing. Okay, and then I'm going to show you the value of the voltage here. Okay, so just see here, the value here, it is 1.398. Okay, so the 1.398 is the Vmax of the input voltage. Okay, 1.398, and here I have seen here 848 millivolt. So if you will convert that 1.398 to millivolt, you will get 1398 millivolt. Okay, so just see here, this is the difference. Okay, this one is the voltage which I have got after the diode, and this one is the voltage which I have got before the diode. Okay, so if you subtract this 848.12 from this 1398, you will get the value of the voltage drop. Okay, because of the diode. Okay, and now if you want to see that this much voltage is if you want to see that this much voltage is the voltage which I am getting from this half of the diode also, then I am going to show you that thing also. Okay, so for that thing I am going to delete this connection, and again I am going to add this connection here. Okay, that will show that yes, both the transformer both the half end of the transformer are giving the same value. So just see here, I have run this thing, and I am going to stop this thing value. Okay, and I am going to again use this cursor here. So just see here, this is at the topmost part of this wave, and here also you can see the 1.398 volt. This part of the transformer is also giving 1.398 volt. Okay, as I have already told you that magnitude of both the half of the transformer secondary winding are same, but they are opposite in the polarities. Okay, so this was the end of the experiment. So what actually you have to do, you have to add a capacitor also here. Okay, so how to do that thing I'm going to show you. Okay, I'm going to delete this connection. Okay, now I'm going to add a capacitor here across this resistor. So for that thing I am going to add here a capacitor. Suppose 1 microfarad is there. Okay, I'm going to just no, I'm just going to keep it here. Okay, fine. So one end of the capacitor I am going to add here. Okay, and the other end I am going to add here. Okay, so no issue if you are connecting here or here or here. Okay, so that would not be giving any problem there. Okay, so now I am going to add one end of the oscilloscope here and the other end of the ground here. Okay, So this I have connected, and now I am going to see the output here. So just see here, I am not going to see any major difference in this pulsating one. It is little bit eliminating the pulsating signal, so I need to change the value of this capacitor. Suppose I am going to use here 10 microfarad here. Okay, done. Now I am going to again run the simulation. So just see here, yes, some part of the pulsating signal are removed here. So again I am going to increase this value. Suppose I am going to use here a value of around 50 microfarad. Okay, so 50 microfarad capacitor I am going to use here. So now again I am going to run here. So here, just see here. Okay, so maximum part of the ripple are removed here. Okay, in this part you can see here in the oscilloscope. Okay, so I am going to just close it. Okay, so this was the final part of the experiment. So now what you have to do in the whole of the part, firstly you have to calculate the value of vrms, okay, vdc in the from the circuit, okay, without the capacitor. Okay, and then you have to find the value of efficiency, which I have already found out here. Okay, but I have found out on 4 volt rms. Okay, at this input point. Okay, so you have to give the different voltage, which I have already mentioned in this lab manual. Okay, in this lab manual I have already mentioned that thing. Okay, now then you have to also find the ripple factor there. Okay, you will find the DC current there also. Okay, by your own. Okay, you have to write the result, the conclusion, and the precautions if required there. Understood? So these things you have to do. You have to take one screen picture of the circuit without capacitor and the other one with capacitor. Okay, and you have to give the output of the oscilloscope also in both the cases. Okay, so use both of that thing, and then in the calculation just to find out the efficiency and other thing which I have already mentioned in this lab manual. Okay, so that would be the final part of the experiment. Okay, so that is the end of the 7th experiment. Thank you for watching.